explained the intensity of electric field due to a current carrying wire yesterday, right? And also Oersted's law we have explained. Today I am going to explain you the direction of the magnetic field, how it can be obtained. So this is a cardboard kept horizontal, and a wire is made to pass through it, right? The magnetic field lines are concentric circles. As this point at the center, you make as many as circles, right? In the beginning you see very near to this conductor, the lines of force are very close, means the circles are very close to each other. Why that? Because very near to this conductor carrying current, the intensity of magnetic field is maximum. Hence, the circular magnetic lines of force will be close, crowded together. When we go away from the conductor, the distance between these circular magnetic lines of force goes on increasing. Why? Because magnetic field intensity is decreasing when we go away from a current carrying conductor, right? So in this case, you see, this is the magnetic line of force. Just like this, if you consider this as a conductor, I hold this conductor with my right hand, such that the curl of the fingers will be the magnetic line of force, and the thumb will show the direction of the current, right? Then the magnetic lines of force will be circular. It is not a single circle, so many circles will be formed, right? As I told you, very near to this conductor, the lines of force is of a very small radius. As we go away from it, the radius goes on increasing, and also distance between the circular magnetic lines of force goes on decreasing. Why decreases? Already I said. This is the condition, right? Okay. So this one, magnetic field intensity direction can be obtained by placing a tangent at a particular point anywhere on the circular magnetic field line. So this is a magnetic field line. See, the arrow mark shows how the field line is like this. This curl is the direction of the magnetic field line. At any point on the magnetic field line, if you place a tangent, that gives you the direction of the magnetic field intensity at that point. See, at this point and at this point, though the field intensity magnitude is same everywhere on this circular path, but direction goes on changing. That also you see. Now, the intensity of magnetic field, its magnitude is given by B is equal to Fm divided means magnetic force. Already you know Fm is equal to QVB sin theta. Therefore, B is equal to Fm divided by QV sin theta. That can be obtained. The unit of B is Tesla, I said. Already we have discussed all these things. Tesla, Newton per ampere meter, and also Weber per meter square. What is Weber? Weber also explained. Weber is the unit of magnetic flux. Dimension of this physical quantity B is m a raised to minus ampere, a raised to minus 1, t raised to minus 2. This is time. So this is about how the magnetic field intensity direction can be obtained from this line of force when the current passes through a straight conductor. Now we are going to explain Biot-Savart law. Biot-Savart's law gives us an expression for the magnetic field at a point due to a current element. What's current element? Current element is a small part of a current carrying conductor carrying a current. See, this part has a length dl that carries current, and that is what is called current element. This law chiefly works on the principle of current element. So magnetic field is a small current element, but it's ideal at a point P. Point P is at a distance r. Make an angle theta. Theta is strongly not marked here. You have to see that this is theta here. So I missed that. I'm very sorry. Right? So the point P is lying at a distance r from the center of this small path ideal, where that means at this point we have to calculate the value of intensity of magnetic field. That is given by dB. Why dB? Because it is the magnetic field. It is small current element. That is given by dB proportional to I dl sin theta divided by r square. This Proportionality sign is replaced by equality sign by putting a constant. K is a constant proportionality. That is K into ideal sin theta by r square. Where K is a constant proportionality whose value depends on the nature of the medium in which the current carrying conductor is placed in, right? So in the free space means error vacuum. In the free space and the SI system, the value of K is equal to mu 0 by 4 pi into 10 raised to mu 0 by 4 pi. Mu 0 by 4 pi, the value is equal to 10 raised to minus 7. See the unit of this quantity K? Tesla meter per ampere. And also where mu 0 is the absolute permeability of free space. Mu 0 is equal to 10 raised to minus 7 into 4 pi Tesla meter per ampere. Also, we have dB is equal to mu 0 by 4 pi into ideal sin theta by r square, very clear. So this is AB sin theta. AB sin theta means the two vectors multiplied, product of two vectors multiplied. If that's a vector quantity, then that can be represented in terms of a cross product. So this is represented of cross product, that is mu 0 by 4 pi into ideal into vector r divided by r cube. Here it was r square. I have applied a whole vector multiplied with the numerator. We are getting ideal. Ideal is a vector because current element is a vector quantity. Current element is considered as a vector quantity. So ideal cross vector divided by r cube. This can also be as equal to mu 0 by 4 pi into I dl cross r divided by r cube. This is how we write the Biot-Savart's law in the vector form. This is a very important formula. This formula can be asked how Biot-Savart's law can be expressed in the vector form, right? B at a point P due to the whole conductor. So this is only for a current element dB. If the whole conductor is taken, what is the total amount of intensity of magnetic field at P distant r away from the conductor is obtained by vector B is equal to, I have written dB here, please right. So what I said, B is equal to the total conductor due to the total conductor carrying current integral dB. Integral dB is integral mu 0 by 4 pi into I dl cross r divided by r cube. So this is also that we are coming as equal to we are getting as equal to this. We can write this as equal to mu 0 by 4 pi into I into L cross r divided by r cube. Or simply you can keep like this also, integral that. Suppose if you want to write a plain equation here, you will write mu 0 by 4 pi into integration is removed. Mu 0 by 4 pi into I into L cross r divided by r cube we can write. Okay, special cases. So this is actually mu 0 by 4 pi into I L sin theta divided by r cube, or ideal sin theta by r cube for a small length, right? So in this expression, if theta is equal to 0, then the point P will be lying on the conductor itself, right? Then dB is equal to ideal sin 0 divided by r 0 is equal to 0. If theta is equal to 90 degree, then theta is equal to 90 degree, that means theta is equal to 90 degree is a line joining the point P makes an angle 90 degree with the conductor. Then dB is equal to mu 0 by 4 pi into ideal sin 90 divided by r square, that is equal to mu 0 by 4 pi ideal by r square. If theta is equal to 180 degree, then also dB is equal to 0. For theta is equal to 180 degree and also theta is equal to 0 degree, in both the cases the point P will be lying on the conductor. That has been already said before. That means when current flows through a conductor, the conductor does not become a magnet, but around the conductor magnetic field is produced, right? So magnetic field is produced. So we have explained the Biot-Savart's law. What principle Biot-Savart's law works? Everybody knows. That is Biot-Savart's law works on the principle of current element. Right. Now we are explaining another new topic. Intensity of magnetic field is a straight conductor carrying current. This is straight conductor carrying current I. Right? There is a point P at a perpendicular distance away from that, where we wish to calculate the intensity of magnetic field. So this is a geometrical method. This geometrical method I am not going to derive that expression. That is not necessary for for you this time. It can be proved that. So these are the things about everything is clear here. Point P is there. X is the conductor current. This also we are using. We are explaining to find the intensity of magnetic field at point P using Bastar's law, right? Bastar's law to use means what is necessary? A current element is necessary. That is, a current element is noted here. This is small part of this conductor carrying current is called current element. So whenever if the question asked to you, the question is asked to you, what? Right. You for using Bastar's law, what do you need? You need a current element because it works on the principle of current element. So it can be proved that the intensity of magnetic field at the point P is given by B is equal to mu0 by 4 pi into I by A into sine I1 plus sine phi 1 plus sine phi 2. This is phi 1 and this is phi 2. When the conductor becomes infinity, phi 1 becomes infinity, phi 1 becomes 90 degree and phi 2 also becomes 90 degree. For an infinite conductor of infinity conductor carrying current, then the intensity of magnetic field at the point P is given by, that is, then phi 1 is equal to phi 2 is equal to 90. The conductor becomes infinity means this angle becomes infinity. Sorry, that this angle becomes 90 degree. Right? Okay. Then the value of intensity of magnetic field at the point P becomes mu0 by 4 pi into I by A. A is the distance of the point P from the center of that. Point P will be at the center. That means line joining. That line will be joining the conductor at the center Q. Phi 1 is equal to phi 2 is equal to 90 degree. The conductor becomes infinity. Did an infinite conductor carrying current I, the intensity of magnetic field at a point on the perpendicular bisector is given by B is equal to mu0 by 4 pi into I by A into 2 pi 2, because sine phi 1 is equal to sine 90, sine phi 2 also equal to sine 90. Sine 90 is equal to 1, 1 plus 1 is equal to 2. That means mu0 by 4 pi into 2 I by A. This relation is a very important relation. So I will derive this relation. This is the intensity of magnetic field due to a current carrying conductor of infinite length at a point on the perpendicular bisector. On the perpendicular bisector, distant A away from the conductor is given by mu0 by 4 pi into 2 I by A. If P lies at one end of the conductor, other point is infinity only, but other point is this point P is here and the other part is infinity. Then what you see, phi 1 is equal to 0 and phi 2 is equal to 90 degree. Phi 1 is equal to 0 and phi 2 is equal to 90 degree. Then B is equal to mu0 by 4 pi into sine 90 plus sine 0. That means that's equal to mu0 by 4 pi into I by A. Right? That's equal to I by A. That is just half of the first result you got. That was mu0 by 4 pi into 2 I by A. While when the point P is taken at very near to the conductor, one side, then the value of B is equal to P at the point P. P is given by mu0 by 4 pi into I by A. And this is the direction of the intensity. Direction of the intensity of intensity at this point P is perpendicular. This is the direction. So I am showing this with the stick. I am showing this. This is the direction, perpendicular inwards. If the current is in the opposite direction, then perpendicular outwards. Always remember that. Because this is the thing like this. Because here, if this is a conductor, you will hold the conductor like this only. You will hold the conductor like this only. That means the direction will be always tangential. That tangent will be perpendicular at this particular point. If you hold the conductor with your right hand, such that the thumb is along the direction of the conductor and curl of the fingers is passing through this point, At that particular point, if you place the tangent, that will be perpendicular to this point. If the current is in the upward direction, then it is inwards. If the current is in the opposite direction, the direction of the magnetic field is outwards. Always perpendicular plane, inward sometimes and outward sometimes. When it is inward, if the current is in the upward direction. When it is outward, when the current is in the opposite direction. So this is the direction of intensity of magnetic field is perpendicular to the plane of the paper at the point P, inwards. If the current is as shown in the figure, if the current is in the opposite direction, that is outwards perpendicular to the point P.